Okay, hello, this is week 9 and this is Energy System Lab 1, and this week we are going to discuss electrical motors and what are the components and how do we diagnose them and fix them if possible. So to start, we would like to talk about electromagnetism, and we will cover that in theory and control for 2 weeks, and how does electromagnetism play a vital role in making a motor. So first of all, we know what's a permanent magnet. That's a piece of metal that's always magnetized, right? So we have a piece of magnet and we have north and south. Okay, that's a permanent magnet. What about electromagnet? Electromagnet is a coil, and as we put current through it, it will become a magnet, and we'll have north and south. That's a good way to put it. So this is electric magnet and this is a permanent magnet. For our kind of motors, we don't use permanent magnet anymore because they are not as reliable and they don't have enough power. With this we can control the power. There are two things that control the power of electric magnet, and hopefully you remember, it's the current and the coil. Two C's. So the coil, how many loops, how many coils do you have? The more coils you have, for this and this, which one is bigger? This is gonna have more magnet, this is less magnet, and also amount of current. So if you have two of the same thing, but one has less current, have less magnetism. Another term we need to know is the rotor and stator. So the rotor is the part that rotates. Makes sense, right? So this is rotating, this is the rotor, and the stator is the part that stays in place. This is the stator and this is the rotor. So it's good to have this terminology down. Moving on. Again, rotor and stator. This is my stator and this is my rotor. It depends on the configuration and how the motor is built, and basically what we are doing, we're trying to push the rotor using the north and south magnetic force of the rotor. Okay, again, if we want to look at it, this is a split phase motor and this is the stator. We can see that the winding here, this is called the winding. This is the winding. This is the winding, and this is what makes the magnet. So those two here are magnet, north and south, and this is my rotor. So it's going to go inside, and you see how it's kind of slanty. That's to offset the motor so it will keep spinning and it will never be in place with alignment with the magnet, because if we have north and south completely aligned, it will stay. Okay, so we have 6 types of common motors. We'll go over them, and you don't have to remember all of them, but they are different. So motor strength is usually measured in horsepower. Two things we need to know: horsepower and also the RPM. RPM, which is revolution per minute. And so there is something called a shaded pole split phase. Permanent split capacitor, so it has a capacitor in it. We have one that has capacitor start and capacitor run, so it has 2 capacitors in it. So you'll see a motor and you'll see one capacitor here for running, one capacitor for start. If you have 2 capacitors, chances are it's a capacitor run and capacitor start. Capacitor start is going to be only one capacitor, which will be in the side of the motor. Doesn't matter where you put it, but probably this is a start capacitor. Why do we have this types, all these types, and why they are so different? Well, it all depends on the application. How much horsepower do we need and how much RPM do we need? Then we have the 3-phase motor. Those are run on different current. They have 3 currents in them: 1, 2, and 3, and it does not need a capacitor. No capacitor. Okay, this is not really clear. So no cap. Let's say cap. No capacitor. Okay. and then we'll have electronically commutated motor, which means that it will change power and speed based on what the current we supply to that motor. So these are some of the tabs we have. We can know that if we have capacitors, it's gonna be if it's two capacitors gonna be one is start capacitor and one is run capacitor. The other one here is could be this is a start capacitor. So open, those are the types. What about open and enclosed? So this is an open motor because the motor is outside and we can see it. That seems very clear. This is enclosed, and in this enclosed it means the whole thing is shielded and it's called hermetic. You see these mostly in ACs, and this part here is the compressor and this is the motor. The reason we have it enclosed is because we don't want any interaction between the outside and the inside of the motor, and usually we run refrigerant, and the refrigerant is very flammable. So, and again, most of these motors are capacitor start, and capacitor do make a spark, so that's a hazard. So for enclosed ones, basically are for ACs, and they are very they have good long longevity because they are sealed, they are not exposed to the elements, and they do the job from the inside. But you will see the capacitor also sometimes in the outside here. Okay, this is a shaded pole motor. Shaded pole motor, they have no start capacitor, so you don't see any capacitor from the outside here. No capacitor. They have very small torque, relatively speaking. They usually come in fans, like a little fan, little inducer fan, little pump, that you'll have a shaded pole because it does not need a lot of torque. It does not need to make a, there's no winding for startup torque, because why do we need the startup? The startup is when the motor, actually, let's say this is the motor, and we have south and north, and this is my rotor and this is my stator. If we have this in north and this is south and they align, it's not going, it's gonna hump, it's going just to hump back and forth, and that will not make it rotate. So we usually need the startup torque to push it out of phase so it will start to rotate. They do not reverse also. That's another characteristic of shaded pole motors. This is a shaded pole, small, non-reversible. Capacitors. So since we will be working with a lot of ACs and some motors, and some of them actually have capacitors. This is the simple for capacitor, and we have two types. We said capacitors are rated in two things, which is the charge, the voltage actually, voltage, and the charge, which is microfarad. So you can see this information here, and basically it just provide a jolt sometimes to kick the motor off phase, out of phase, so it will start to spin, and that's basically the job of a startup capacitor. If you have two capacitors, one of them is to start the motor, the other one is to improve performance. There is a big configuration inside that will change the ability of the motor to run in a smoother, more efficient way. I'm not going to get into it, but it's used to be continuously running as the motor is running. So capacitors, they are measured in farads or microfarads. They are oil filled when it's from 2 to 80 microfarads and 240 to 50 volts. Other than that, it could have different filling. Sometimes it's wool, sometimes kind of rock wool, different kind of material. They're used for startup, for running, and they are very susceptible to heat. So if it gets overheated, probably it will go bad. Bulging, when it's bigger, if it gets like bulgy, this is the cylinder. Oh, hold on. If this is a cylinder here, this is bad. Oh, eraser. So if you have a cylinder here and it starts to bulge, that means the capacitor is going bad. For replacement, you want to have almost exact replacement or within a percentage plus or minus of the original if you cannot find any. And nowadays they have a lot of capacitor where you can have different kind of output. And for testing, if you test for resistance, you get 0, and it should be tested actually with the setting of capacitors. So they have a specific capacitor tester. This is if you want to use the ohmmeter, which we're not going to do here. We have, at this day and age, we have capacitors testers. So split phase motor, that's a different kind of motor. Again, this is my squirrel cage here. Stator stays in place, and this is my bearing, and this is my rotor. So they are used, they have high startup torque. It has a split phase. Usually have a belt operation, so you get, as you guessed it, probably it will be connected here with a fan, a pulley, and a fan. EMF is the electromagnetic forces, so it has very high electromagnetic forces to spin that motor. And this here is a cooling fan to cool the motor as it runs, otherwise it will overheat. Some of them have centrifugal switches, which means it will, this is the centrifugal switch. The centrifugal switch, what it does is it opens up when the motor reach 75% of the maximum RPM, and this is the frequency, which is 60 Hertz. Okay, this is the motor with the running winding. So this is the, if you can see, there's different kind of winding. There's a start winding and there's a running winding. So the start winding will engage, then as we reach the desired RPM, it will, the centrifugal switch will cut off the winding, and the motor will keep spinning, but it will not increase the speed. So the startup winding here, going to these loops here, will add more speed, keep adding speed until we reach the amount of RPM we need, then it will cut off the startup winding. And you can hear it click usually in a lot of those motors. This is the centrifugal switch. As you can see, this is the contact, and as we spin, we produce a force that will push that switch, this switch upward, and by doing so it will click, it will pull this up, and it will disengage the switch, and this will disengage here my startup winding. So they're very, very reliable, and the bearing could be an issue. The bearing is what holds the rotor in place. This is the centrifugal switch, and there's also a limit switch over here for the, in case the motor seized and it starts to overheat, the limit switch will cut off the entire winding. When we talk about winding, we always talk about those braids of copper wire going through. So this is a capacitor induction run motor. This is my centrifugal switch run, and this is represent the winding. So this is the startup winding, and this is my start winding. This is running winding. Okay. Another type is the permanent split motor, which has moderate torque, and again different kind of winding inside of it to alternate the speed and also alternate the RPM. RPM is the speed and the torque as well. PCM is the schematic for it. Again, it has a running capacitor with them. This is the running capacitor, and these are my windings. And this is inside a hermetic compressor. What does that mean? It's that cylinder we saw before with the motor and the compressor inside. So in the lab, which we are not going to do live, but it's what you need to do is get a motor and check if it works or does not work. If it works, that's fine. Then we'll take it apart and put it back together, and hopefully it will work. If it does not work, we will try to diagnose. First thing you do to check if it doesn't work, we'll check the amperage and compare it to the label. So you go to the label and say how much it's supposed to draw. 1.5 amps. Okay, that's good. If it's drawing 1.7, what does that mean? Something is stuck. When the motor is stuck, it will draw more amperage. If it's drawing too little amperage, could be also a problem. Maybe there's something wrong with the winding. Also, you can check the motor visually by looking at the winding and see if it's burnt or if it seems kind of flimsy. Or you can also smell when when the winding has burnt or the insulation between the winding is burnt. We can check the capacitor using capacitor testing, and also we can test the winding for resistance. It says here resistance, so we check the resistance, and that will also enable us to check the continuity for all the resistance and make sure that all of them is continuous. We will record the information and wire it together and put it together again and see if it works or not. So I will post some questions about this lab, and hopefully you remember the main things, and I'll also post a few videos from online. All right, thank you.